speaker is Scott Hansen. He's currently the Condensing Heat Exchanger Technology Development Project Manager at NASA Johnson Space Center's Thermal System Branch. Prior to his work with condensing heat exchangers, he successfully developed water-based phase change material heat exchanger. Scott graduated from Texas A&M with a master's in mechanical engineering in 2012 and holds a bachelor's degree in finance from the University of South Dakota. His presentation is Laser Processed Condensing Heat Exchanger, Test Article Design, Manufacturing, and Testing. Ready when you are, Scott.
Hey, can you hear me now? Sorry about that.
Yes.
Okay. Sorry. Yeah, thanks, Jesse. My name is Scott Hansen, and this is for, this presentation is for test article development and manufacturing of and testing of a laser process heat exchanger. We've been working on this project for probably about 4 years. Starting with little coupon level tests and working our way to this test article design. This is the first subscale test article of a laser processed heat exchanger that we've made. So excited to share the work. I want to acknowledge the other co-authors on this team, Sarah Wallace and Tanner Hamilton at JSC, Dr. Dennis Alexander, Dr. Craig Zolke at University of Nebraska-Lincoln, and two PhD students, McRoth, Aaron Ediger, also at UNL, and then at Criari and Adari, their sister companies. We have Mike Eisenson, Dr. Mike Eisenson, and John Sanders. So thank you for those co-authors. I'll jump right into a problem statement and our technology overview. Our condensing heat exchangers are really a critical function of closed loop life support systems. They serve a dual role in that they provide sensible and latent cooling for the vehicle. So that sensible is just cooling the air, and then the latent aspect of it is removing the humidity from the air. And it's roughly about 50% of the reclaimed water on ISS actually comes from condensate. The other 50% is from urine. So it actually serves a much bigger when I first started, I was surprised that it was that much water that actually comes from these systems. So it serves a pretty big function. The current technology that we use to control the sensible and latent cooling, it uses a hydrophilic coating to gather condensate and control microbial growth, also in conjunction with a monthly dry out. As that water condenses, it wicks out onto the surface because of the coating, and then there's slurper bars embedded into the heat exchanger that suck that water out in conjunction with an active water separator. There's 3 big problems with the current technology. One is coating longevity. Hydrophobic contamination causes that hydrophilic surface to turn hydrophobic, and you get water carryover, so water spits out of the heat exchanger and potentially damages downstream components. Because of that, your heat exchanger ORU has to be uninstalled, and then bring it back down to earth, refurbish it, and then send it back up. So, and that's a very significant resource drain on doing that process. Second concern is microbial and fungal growth concerns. Current coating uses some silver oxide to mitigate microbial growth. It also has to be dried out on a monthly basis, and we want a heat exchanger where we don't have to go through we never have to dry it out again to prevent that biofilm from forming. And then the third one is that current coating reacts with airborne contaminants, which produce potential harmful substance that degrades the filters in the WPA. So and which WPA is the water processor assembly. So we're really looking at this technology to enable long duration space flight and reduce up mass and down mass. And really our goal is to create a more robust condensing heat exchanger. The technology overview, there's a picture of our subscale unit on the bottom right there. It's a dimple plate heat exchanger, which replaces the typical plate fin heat exchanger. All of our condensing surfaces are actually 99.95% pure laser processed silver. The laser processing, which I'll be talking a little bit, allows for increased service area and laser production. Adari and Creari really owned this manufacturing design and process. UNL did the laser processing. We sized the heat exchanger is sized so that it ejects condensate from the outlet of the laser process heat exchanger, and then we're developing an active water separator that's downstream of the condensing heat exchanger to remove that condensate that gets ejected, so it doesn't damage anything downstream. There's two types of water separators. There's an active one that's being developed by Paragon called Cosmic, and then there's a water capture device being developed by Sierra Nevada, which is a passive water separator. In terms of the design and manufacturing, I mentioned that Creari and Adari do the design and assemble. UNL does the laser processing, and then we've done the testing. So we've got quite a team, and a really great team to work with that have done a lot of wonderful work in developing this technology. To give you an idea of how the internals of the heat exchanger look, it's basically several packets stacked on top of one another, and then there's an overall manifold that goes that envelops the entire packet assembly and holds it together. So this is a picture of the packet assembly. Video rather. Each packet is made of it's a stainless steel inner core and thermal interface material outside of that, and it's silver outer core or packet that all get laser welded together, and each one of those packets get joined together by this little silver, or it's a stainless steel ring, and those get laser welded together, and those packets join up one on top of another, and then all of those packets get assembled one on top of another in this video here, and then there's an outer manifold that holds the whole thing together. So our subscale unit utilizes 8 packets. A full-scale unit would utilize 142 packets. It's a line of sight designed for an ISS flight unit. So we did some thermal analysis. Adari did, and a Creari to size this unit. We wanted to keep the air side pressure drop below 1 inch of water. We did assume laminar flow. We were flowing through it. About a full scale unit would flow through about 300 CFM, 250 to 300. Our liquid side pressure drops, most of the pressure drop was accounted for actually in the manifold. And we have some good data from our testing of the unit on our ground, the pressure drop through the subscale heat exchanger. And then in terms of our air side heat transfer and condensation modeling, it was an Excel model that Creari developed, which assumed a convection coefficient, a condensate heat transfer, assuming some inlet temperature for the airflow, and then conduction through the wall. We did use that Nusselt number based on laminar Nusselt number of a little over 3.5 based on laminar flow constraints and a constant wall temperature for that cell. It was a Excel model that we ran and sent through the heat exchanger in 1-inch steps. There's the rough flow length of the heat exchanger is about 8 inches. And so we determine the bulk gas temperature in the next cell based on that enthalpy balance change in that cell. The laser processing, probably find the pictures probably more interesting than, I find them really interesting. So there's, we looked at, and this is prior year's work as well, we looked at several different types of surfaces and laser processing patterns. There's direct writing, dual pulse, and low energy laser processing. We went with the dual pulse laser processing for this. We wanted to make sure, and we did a lot of SEM and 3 surface analysis on these surfaces, and we wanted to confirm that structure formation of this silver was consistent. We wanted to look at and make sure that our laser processing doesn't punch holes into that silver substrate. We were using about 6/1000 inch of sheet of silver there. And then I've got some pictures on the next slide here, next couple, to verify how our laser processing was going. So this is all the dual pulse. This is a dimple that was formed in that silver sheet. You can see we're getting pretty good patterning over our surfaces. This is a zoomed in picture in this bottom left-hand corner of that transition between a flat plate and up through the dimple. And we're getting good microstructures on that surface. What we don't want to happen is on this top right or the top left picture on the top right of that dimple, you can see that there's no laser processing. It's kind of a bare area in there. We didn't want to see that. And so we made some changes. UNL made some changes to ensure that we could get that and process both on this, the convex side, and then the picture on the right-hand side is the negative side. So it's a concave side. We also wanted to make sure that we weren't punching through the dimples. The thinnest section on the sheet is the area where that transition of that dimple occurs. So UNL did some amazing work, and they actually sliced one of the dimples in half and SEM'd the cross section of it. So this is a picture of the dimple sliced in half. The middle picture is zoomed in on specifically that transition. It has laser processing both the positive and the negative side. And as you can see, there's still meat in the silver, so we're not punching any holes through there. And then we also wanted to make sure that laser processing could occur on our weld beads. The weld beads occur around the perimeter of a packet to seal them together, to join them together. And as you can see from the picture, we're getting good coverage of laser processing on the weld beads. So UNL, Adari built it and they shipped it to NASA for testing. We got it about, I think it was October or September of last year for 6 months testing. And 6 months is we consider that a long duration testing, or the beginning of a long duration test for a condensing heat exchanger. We built this test stand up, which is basically we have a fan blowing air through this ducting. The laser process heat exchanger is positioned here so that as you flow through it, the water drips down out of it. And then we have a instrument and a funnel, instrumentation on the outlet and a funnel to catch that water. And then that airflow returns back to the blower. So it's a closed loop system. Our big test objectives were 1, to look at our water quality, 2, to look at our micro and fungal growth, and 3, to look at our heat transfer and compare it to the model. So the results of it, in terms of our water quality, we got water quality samples about once every other week for the duration of the test. Our goal was, our criteria summary for this was prevent or reduce introduction of contaminants into the condensate water over the lifespan. in that lifespan, our goal would be 5 years. Our threshold would be 3 years. So we could really tell right up front whether we were going to get any adverse effects from the testing air that we were using, which is just a lab environment, but also stuff coming off the heat exchanger. And we worked pretty closely with Lane Carter at Marshall to look at our water quality. And we looked through pages and pages of water quality data from this. And basically everything looks acceptable to the WPA for the environment that we were testing in, except we have a gigantic, just a massive concentration of silver ions when we first start testing the laser process heat exchanger. It's roughly about 30 to 40,000 ppb when we start testing before it drops down. So the picture on the right-hand side is the elapsed days, and the concentration of that silver ion is on the left end of that axis. And you can see how it drops down over time. We did do a period of accelerated testing where we just flowed water, about 200 gallons, over the surface. So that's one of the reasons why there's a big drop in between days like 40 and 50 there. So in order to solve this problem, it's too high a load for the WPA. So we likely that if we were to integrate this into the ISS, we'd have to do some type of initial condensing flush before we would deliver this over for flight on the ISS. But other than that, all of our water quality samples from our testing meet our performance goal. We don't anticipate that there would be any problems with this unit in terms of water quality to the WPA. Primary reason for that is because it is just, you're condensing on laser processed silver. There's no chemical coating that's used in this device. For our microbial growth, we collected microbial samples from the test stand on a weekly basis. And then we also sprayed every other week into the test article. We sprayed 10 to the 4 bacteria and 10 to the 3 fungi. The 3 bacteria that we used are listed there. I'm not going to try to pronounce them. And then the 1 fungus is this Aspergillus niger listed there. And the counts that we found are on the right-hand column here. There's elapsed days, bacterial count, and the fungal count. So we're getting very low levels of bacteria and fungus recovered, which it really indicates a high level of microbial control over the whole duration of testing. We did pick up a few here and there, but it was nothing at an alarming level that would cause us to take an action like a dry out. Our criteria summary and goal for this was to prevent or mitigate formation of microfilm or microbial growth in biofilm. Our goal was to keep surfaces below and water cleanliness below 10 to the 3 CFUs per mil. The threshold was 10 to the 4 CFUs per mil. And we were able to do that, and we think that's primarily attributed to the silver ion concentration in that condensate. And so that's why I put up the chart here again. We have pretty high levels of silver ions in the condensate. And so we think that the silver ions definitely help. There may also be part of the surface geometry of our condensing surfaces that may also help prohibit microbial growth in biofilm. In terms of our heat transfer, this chart we have tons of data points from this, but this chart summarizes it nicely. Our experimental heat heat load that we got from testing is here, and we'd ideally expect that to line up with our simulation. We were slightly underperforming it with these red dots here. The test points that we took are from this right-hand side, this table right here. So we plotted those test points on it. They're slightly underperforming where we'd expect. And so the original model that we had predicted we need 91 packets to meet the full-sized heat load. And our future plans to increase the heat transfer is to increase that to about 142 packets. So in conclusion, we successfully tested and built a laser processed condensing heat exchanger subscale unit. We tested it for 9 months or 6 months. During that 6 months, we got a lot of valuable insight into the operation of the unit in terms of water quality, microbial growth, and heat transfer. It meets our water quality standards, but we did identify an operational procedure that we'll have to do before we deliver this unit to ISS for flight and integration into the CCAA. For our current testing durations, our microbial growth and fungal growth meet our performance goal. So it creates a really clean condensing surface, or maintains a clean condensing surface, I should say. And then our heat transfer was slightly underpredicted in our model, which just results in having to have more packets, 142 versus 91 originally. So our future plans for this, one of the things we really want to look at is, instead of, I mentioned having the individual packets is made up of a silver or stainless steel packet enveloped with thermal interface material and silver. And we want to look at electroplating silver directly onto that stainless steel packet. That would decrease the time it makes, the manufacturing time, the cost, and just the complexities in building up a full-scale heat exchanger. So we want to investigate that and then move into building a full-scale laser process heat exchanger and test it. And ultimately, we have our eyes set on an ISS demo with one of those integrated water separators, either from Paragon or from Sierra Nevada. So I think that concludes my talk. There's a lot of people I want to thank. I mentioned our co-authors already, but I also want to give a shout out to our NASA interns, Riley Dalton, Dan Devaney, Thomas Gross, Alexandria Lanise, and Aina Noorani. All of these have been, over the past several years, have been involved some way, somehow in this project. So I really want to thank them for their time on and developing this concept. And then I listed my email down there. If you want to email me any questions after this, feel free to. Otherwise, I'm open to take some questions right now.
All right, thank you, Scott. There is one question on the chat right now. Did the surface structures change the wettability of the silver?
So, yes. The silver is it's hydrophobic, and from my understanding of when they first process the silver, it is hydrophilic. But the silver is very reactive with contaminants in the air, and it turns it hydrophobic. And so they're actually super hydrophobic surfaces when we get them. And the thing about this technology is it doesn't matter if it's hydrophobic or hydrophilic. We just want water to get spit out of the condensing heat exchanger. So we really don't care if it's hydrophilic or hydrophobic. And that's by design. We just want it to spit out water and not be concerned about air quality and contaminants in the air.
All right. How did you come up with the thickness for the for the silver? I think it was 6 mil.
Yeah, we looked at processing several different thicknesses. I think we did like a 4, a 6, and an 8 mil. We had been doing 10 mil sheets in the past, and so we wanted to see what we could do. So we sent some to UNO for laser processing, and they did similar things to cutting those 4, 8, and 6 thousandths of an inch in half, and then looking at it. And I think we could get away with doing a 4 mil sheet or 4 thousandths inch sheet, but we decided to stay with a 6 thousandths inch sheet out of an abundance of caution. And so the plated design, we're going to be evaluating, like, in order to save weight on the device, because silver is heavy. We want to. We're going to be going through that process again, only with the electroplated design, to see what minimum thickness we can get away with.
Okay. I have another question from the chat. Did you notice any fouling or potential fouling during long-term use?
Is that micro or bio fouling? If it's micro or bio fouling, we didn't notice any fouling.
All right. Let's see. So what was the quality of the water that you used? Was it deionized or distilled, or just
So we were condensing it just in a lab environment, so it was just whatever came out of the air. We did put humidifiers. We actually ended up building basically a cage around the test device to test it at higher, or the test setup. We built a cage around that, and we put humidifiers in that room, and we just used regular tap water in that system to humidify by the air.
All right. Well, we're coming up on the end. Thanks a lot.
Thank you.